Good morning to all of you. Today I will deliver lecture number 15 of Unit 2 of Chapter 1. So in today's lecture I will discuss more about results regarding relation, equivalence relation, congruence relation, compatible relation, all these very important results. So let's start. Definition. For any arbitrary relation on semigroup S, we define RC as XAY, XBY such that XY belonging to S1 and A comma B belongs to R. See, this is RC relation. We define this is relation RC. Basically, we define a relation RC on a semigroup S. R is any arbitrary relation on a semigroup. Then RC is defined as a pair XAY, XBY, such that XY are from monite S1 and A, B is from R. So whenever A, B from R and XY from X1, we say that XAY, XBY is in RC. Correct? Now see the lemma. Lemma 1.5.5. RC is the smallest left and right compatible relation. Left and right compatible relation. Containing R. So basically we have to prove that RC is the smallest left and right compatible relation containing R. Of course on a semigroup S, compatible relation on semigroup S containing R. So basically we have to prove two things. First we have to prove that RC is what? Left compatible and right compatible. Then after that we prove this is the smallest left compatible, right compatible, and also it is contain R. So first try to think about that, how it contains R. See, proof. Take any A comma B belongs to R. Then A comma B can be written as like this: 1 into A into 1 into 1 into B into 1. We can write like this or not, because you see 1 is identity element, so 1 into A into 1, 1 into A into 1 is what? A. Similarly 1 into B into 1 is B. So now you see when A comma B is in R and XY is in S1, then XAY comma XBY goes in RC. So here when A comma B is in R, then 1 into A into 1, 1 into B into 1 will certainly go in RC. by definition of RC. Correct? So it implies what? It implies that R is contained in RC. Correct? Now what we have to prove? We have to prove that RC is left compatible and as well as right compatible. So how we prove RC is left compatible? That is, we have to prove that now we show that RC is left and right compatible. For this, let for any basically what you have to prove, you have to prove RC is a left compatible. So you take a pair in RC and you have to multiply by left one side, that is to show compatible. What we have to do, think about that. So let for any you just write like this, for any C S T belonging to S, you just take any C, S, T belongs to S, such that S, T belongs to where? RC. Correct? Then there exists XY belonging to S1 such that S will be what? You see, S will be what? S will be X when S, T belongs to RC. Take any C, S, T belongs to C. So there exists X, Y belongs to S1 such that S can be written as C is equal to XAY and T is equal to XBY, where A, B goes in R. Because when S, T is in RC, then S, T should be like this, S should be like this, T should be like this, where XY are in S1 and A, B is in R. Now we calculate CS. So CS will be what? CXAY, and it can be written as CXAY, and T is equal to similarly CX into BY, and A, B belongs to R. So this is the situation. You see CS is written as CX into AY, and T is written as, and CT is written as CT, and CT is written as CX into BY. And of course when X is in S1, then CX is also in S1. So CX here, CX comma Y both are in S1. It means what? So it implies what? So CS comma CT will go where? In RC. Because you see the definition of RC. RC contains those members any xay comma xby, it contains such type of element, such that the end element should be from, for the first slot if you see, end element should belongs to S1. For the second slot you see, end element should belongs to S1. And pair AB should be in R. Here the situation is same. AB is in R, correct, and an element Cx and Y, both end elements are in S1. So we can say that Cs comma Ct belongs to RC. Similarly, SC comma TC also in RC, and it means what? That is, RC is left compatible, and here that is RC is right compatible. So basically we have proved that RC is compatible relation. If R is any arbitrary relation, correct, so then RC is left compatible relation and right compatible relation, and therefore it is compatible basically. So RC is compatible relation, left compatible and right compatible relation on a semigroup S containing R. So we have proved this thing. Now what we have to prove? We have to prove thus that it is the smallest compatible relation. So for this we assume that let T be another left and right compatible relation containing R, correct. Then what is our claim? Our claim is that R phi is contained in T, correct. So you assume that take any basically T is another left compatible relation containing R. That is what we have. We have basically R contained in T, correct. It implies that A comma B, if you take for any AB belongs to R and R is contained in AB, so AB goes in T, correct. So AB is in T. Then XAY comma XBY for every XY belonging to S1. XAY comma XBY goes in T, since T is both left and right compatible. See, as it is given that relation T is both left and right compatible, so if A comma B is in T, then if you multiply by left side, that is XA comma XB again goes in T, and also XAY comma XBY again goes in T. Why? Because T is also right compatible also. So it means that for every XY belonging to S1, XAY comma XBY goes in T. It means what? Whole RC and every element of RC is in T. It implies what? So it implies that RC is the subset of T. So in this way we have proved what this is our claim. So we have done. So it means that RC is the smallest left and right compatible relation on a semigroup S containing R. Now you see lemma 1.5.6. Lemma 1.5.6. Let R S be relations on a semigroup S. Let R S be relations on semigroup S. Then just I am writing down, we have to prove this. R subset of S implies RC is contained in SC. Second, RCC is equal to RC. Third, R inverse C is equal to RC inverse. Fourth, R union SC is equal to RC union SC. Fifth, R is equal to RC implies, re-implies R is left and right compatible. So these are the parts which we have to prove. Sorry for the disturbance. So we have to prove these 5 parts. See, easy parts are there. These are easy parts. R is left and right compatible. So R is subset of S. We have to prove that RC is contained in SC. Correct? Okay. So you take, if you prove first part, take any CD belongs to RC. It implies what? There exists XY belonging to S1 and AB belongs to R. And of course it goes in S such that CD is equal to such that C is equal to XAY and D is equal to XBY. Correct? Now you see, we have to prove that when A comma B goes in S and XY in S1, so naturally it implies that C comma D will be in SC because AB is in S. So it implies that RC is a subset of SC, correct? Now see the second part, RCC. One part is trivial. Basically we have to prove that two sets are equal, correct? This is set A, this is set B. So we have to prove set A is contained in set B and set B is contained in A. Then only both set A and B become equal to each other, correct? So you see, if you assume this as, say if you assume for example S it is. So situation is that S is equal to SC. S is equal to SC, and we know that SC always contain any. We have already seen that R is contained in RC, isn't it? So we already know that RC is contained in RCC. This part we have already done because when R is contained in RC, then of course RC is contained in RCC, isn't it? This is already done. This part is done. Now we have to prove the converse part. We have to show RCC is contained in RC. Basically we have to show this, correct? So for this you take any element here in RCC and show that it goes in RC. So you take the element here. So take any it implies that xy belonging to S1 and A comma B belonging to RC such that C is equal to XAY and D is equal to XBY, like this. Now you see, when A comma B belongs to RC, it means what? So A comma B belonging to RC means, it implies what? It implies there exists XY belonging to S1